So you remember from Tuesday, right? We're working on solving the harmonic oscillator, okay? And so one step there was to figure out about the ladder of states, right? That there is a sequence of states which have specific energies, right? And we figured out that you can get from one state to another by applying a raising operator, A plus, to go up one level, or a lowering operator, A minus, to go down a level, right? And then this difference of energies would be H bar omega, right? Where omega comes from the spring constant and the mass. And then we did a little calculation to figure out what's the bottom of the ladder. And we figured out the energy at the bottom of the ladder, which is 1/2 h bar omega. And we figured out what's the wave function at the bottom of the ladder, which is this Gaussian function. Okay, so now let's see what the wave function looks like, and then let's see how we can use the raising operator to go up the ladder. Okay, so that's what is shown here in this Mathematica demo. Okay, so in this demo, I start by defining these operators, A minus and A plus. Okay, and so these operators are ready for some test function as input. Okay, and then whatever the test function is, the operators produce something. Okay, so A minus produces H bar times the x derivative of the test function plus m omega x times the test function, and all of that divided by this square root, okay? And it's simplified with the assumption that all these parameters are positive or real. That's A minus. A plus does the same thing, except just with a negative sign right here. The Hamiltonian is also an operator, which can act on a test function, okay? And what it produces is minus h bar squared over 2m times this second derivative of the test function plus 1/2 m omega squared times x squared times that test function. Okay, so any of these things are operators that can take a function as input and they produce a new function, right? So just to see an example, right? If my function is x squared, whoops, sorry, I typed in the wrong place here. If my function is x squared, A minus acting on x squared, that produces this complicated thing, right? Or A plus acting on x squared produces this function, right? Very similar except for the plus or minus sign, right? Or the Hamiltonian acting on x squared produces this thing, okay? Now, you can see that the Hamiltonian acting on x squared does not produce something times x squared, right? So that shows that x squared is not a solution to the time-independent Schrodinger equation, right? We can't just guess a solution that easily. Okay, so we did find the lowest solution, right? We found the solution corresponding to n equals 0, okay, the ground state. So that's what I'm going to demonstrate here, okay? So here, for the state number 0, we found from the calculation yesterday that the energy En for n equals 0 is a half h bar omega. Right? And we found that the unnormalized wave function number n for n equals 0 was this thing, right? An exponential of minus m omega x squared divided by 2h bar. Okay, so that's our bottom of the ladder. Now, we still have to do all the things that we did before for the particle in a 1D box, right? Like normalizing the wave function. Okay, so we want to check the normalization by taking the integral of the complex conjugate of psi times psi for x from minus infinity to infinity. Okay, so that integral gives this constant. Okay, now we want to normalize the wave function so that that integral will be 1. Right? So we can achieve that by dividing by the square root of that constant. Okay, it's just like you did in the first homework that I sent back to you last night. Okay, so here we do it. Okay, so we take the unnormalized wave function divided by the square root of the integral that we got. And so here's the normalized wave function. There. Okay. Now, maybe we want to check whether this normalized wave function is truly a solution of the time-independent Schrödinger equation, right? Let's check it, okay? So I could say, what is the Hamiltonian acting on psi 0? Okay, and so we look at this and say, oh yeah, that is something times psi 0, right? It's just a constant times psi 0, right? So it's unlike when we put in x squared as the input, right? And we didn't just get something times x squared, right? But here, when we put in this input, we do get something times the input, okay? And then by comparison, E0 times psi, psi 0, that is a half h bar times psi 0. These things look pretty similar to each other. Are they exactly the same? Well, I think so, but I better check. So one way to check is to say, let's calculate the difference. Okay, so if I say, what is this thing minus this thing? Is that 0? Well, I'll tell Mathematica to simplify it. Simplify this difference. Well, Mathematica doesn't know which parameters are positive, right? And so it has trouble with these fourth roots. So I'll tell it to make this whole bunch of assumptions about what's positive. Oh, good. Now it's 0, that difference. Okay. So that's the code that I was doing in this line, right? So it's just a check to make sure that Schrödinger's equation is really satisfied. The time-independent Schrödinger equation is really satisfied. Okay. So now, what does the function look like? Okay. So here's a plot of it, right? And to plot something, I have to put in numbers, right? So I'm putting in numbers, arbitrary numbers, that the mass is 1 and omega is 1 and h bar is 1. Okay, so that is true in some weird system of units, not SI units. So with those numbers, the wave function looks like this. Okay? And so this is a Gaussian function, right? So it has a peak right at x equals 0. And then it goes down and it sort of asymptotically decreases toward 0 as you get out to large x. So you can now think about, how does this compare with the lowest energy state for the particle in a 1D box, right? For a particle in a 1D box, you remember that the lowest energy state was a sine wave, right? That goes up from 0 and has a max in the middle, and then it comes back down to 0. Right? So this looks similar to that, right? It comes up, it has a max, it goes back down. The difference is that for the particle in a 1D box, the wave function really goes to 0 at the two ends, right? Because the potential energy goes to infinity. Right? Here, the wave function doesn't really go to 0 exactly at specific finite values, because the potential energy doesn't go to infinity all at once. Right? The potential energy gradually gets higher and higher. And so the wave function gradually gets smaller and smaller. But it's an asymptotic decrease. And so the probability of having a particle way out from the origin is extremely small, but it's not 0. So this is the ground state, the lowest energy state. Okay? If we want to go up to the next highest state, let's do that. Okay, so suppose we want to go one step up the ladder to n equals 1. Okay, so the new energy, the energy for n equals 1 is going to be the energy for n minus 1, so 0, plus h bar omega. Okay, so that's this 3/2 omega h bar. And the corresponding wave function, not yet normalized, is this. It's just a plus acting on the wave function that I found before, okay, acting on psi 0. So here it is, okay? And so you can see that is the same exponential factor times x times various constants. Now for the constants, well, we really better make sure that this function is normalized, okay? So let's check that, okay? We'll check it, and so we take psi star times psi and integrate that from minus infinity to infinity. Oh, that makes 1. Good luck, it's already normalized, right? But still, I'm just copying and pasting my code, so I'm dividing by that. So I'm dividing by the square root of 1, not that it matters. So the normalized wave function is this thing, okay? Once again, I can check that it's really a solution for Schrodinger's equation by saying, what's the Hamiltonian acting on this function minus the energy times the function? And we'll tell Mathematica to simplify that difference, assuming all these things are positive. Oh, good, it comes out to be 0, right? So that really does satisfy the time-independent Schrodinger equation. Okay, so now what does this plot look like? Well, you can see it it is asymptotically close to zero for large x. And then when you get close, near to zero, near to x equals zero, the function goes down. Here it's negative, then it comes back up. It has one node right there at the origin. And then it has a positive peak and comes back down. Okay. You can compare this with the first excited state, that is the second lowest energy state for the particle in a box. Okay, you remember that one, it's zero, and then it has a negative peak, and then it goes to a node right in the middle, and then it has a positive peak and comes back down. So this is kind of similar to that, except that, again, it doesn't go exactly to zero at specific boundaries. It just goes gradually, asymptotically to zero as x goes to plus or minus infinity. Okay. You guys good with these things so far? Okay. Right, so you want to be able to think about the wave functions both algebraically and also visually, right? Just to see what the function looks like and see how the extra going up and down makes extra kinetic energy, right? So it's a higher energy state. And also you can see that the wave function is pushing a little bit farther away from zero in this case than it was in this case, right? This is mostly concentrated around zero. This is a little farther from zero. So this one has more potential energy as well as having more kinetic energy. So now we can keep on going. So now I can just keep copying and pasting the same code to go to higher and higher steps on the ladder. Okay, so I got excited about that. I just kept doing it. Okay, so here is n equals 2. Okay, you can see then that the wave function looks like the same exponential factor times a quadratic polynomial, right? So something times x squared minus a constant. And the plot of that looks like this, right? It has one extra node, that each time you go up one step, you add one extra node. Right? So more kinetic energy. And it's also a little farther from x equals 0, right? That the bulk of the wave function is a little farther from x equals 0, so more potential energy also. I just kept going with this. How many of these did I do? Here is state 3. Okay, so in state 3, the wave function looks like the same exponential factor always, times now a cubic polynomial. It's cubic because here's an x, and then here's an x squared minus constant, right? So that makes a cubic term and a linear term in x. And it has one more node, okay? And maybe I'll kind of fast forward through more of these things. So for n equals 4, one more node, all right? And getting a little more spread out. N equals 5 continues that pattern, okay? You'll notice that all of the even ends are even functions. That is, they're symmetric between the positive x side and the negative x side. And all of the odd ends are odd functions. That is, the function for positive x is the negative of the function for negative x. Okay, and so here's n equals 6. I think I went up to n equals 7. Okay, up to n equals 7, right? So with each step up the ladder, we go to a higher energy and we go to more and more nodes, right? So here's a summary of all the pots, right, to compare with each other. So now we can keep on doing all the stuff that you're familiar with from the particle in a box, right? So we can calculate expectation values, the same as you're familiar with. So I made a little loop here to calculate expectation values of things, all right? So for each state, I calculate what's the average x? It's always 0. What's the average x squared? It's not always 0. It keeps getting bigger, all right? And so that means the potential energy keeps getting bigger because the potential energy is a half kx squared. What's the average momentum? That's always 0. What's the average momentum squared? That's not 0. That keeps getting bigger when you go to bigger n. So the average kinetic energy is the average momentum squared divided by 2m. Okay, so that keeps getting bigger. Okay, so you'll notice, incidentally, that the average potential energy equals the average kinetic energy for each of these states. That is actually the same as what you might remember from a classical harmonic oscillator, that the average kinetic energy equals the average potential energy. Okay. Then the average of the Hamiltonian is the sum of the average potential energy and the average kinetic energy. So it keeps going up in steps of h bar omega. So that's just like what we found when we were making the ladder of states, that there ought to be steps of h bar omega. And then we can also get out, the uncertainty in x and the uncertainty in momentum, right? The same as you've done in your previous homework. And then take the product of those things to see if it's consistent with the uncertainty principle. If we do that, we can see that the product of the uncertainties is equal to h bar over 2 for the lowest state. The bottom state is right at the limit for the uncertainty principle. The higher states have bigger products of uncertainties, right? So they are consistent with the uncertainty principle, but they're not at the limit. They're well above the limit. Okay, so each of these states is some polynomial times the same exponential function, right? That's something I showed you as we were going along, right? And so the polynomials are getting to be higher and higher order, okay? So for state number 7, right? Here we have an x times this stuff, which is an x to the 6th, x to the 4th, x squared, and constant, right? So it's a 7th order polynomial, right? So for each state n, we have an nth order polynomial times the same exponential thing. There is a name for this family of polynomials. These things are called Hermite polynomials, okay? Or it's some constant coefficient times a Hermite polynomial, okay? in quantum mechanics, we are going to encounter a lot of these special functions that are named after somebody. The textbook goes into a lot of detail about these special functions. I don't find that information to be really that interesting to me. I mean, I'm never going to tell you to not learn something, because then they would, take away my union card for the faculty union, right? But I would say that, learning about the special functions that are named after people is not a super high priority on the list of things that you want to learn. There's just one kind of special function much later in the semester that's really worth learning. I'll tell you about that later when we get to it. Okay, but these are Hermite polynomials. The book tells you all about Hermite polynomials. Mathematica actually knows about Hermite polynomials. And so I can tell Mathematica to make a table of Hermite polynomials. And sure enough, those come out to be the same thing as the solutions that we get from applying the A+ operator multiple times. Okay. Now, these, you remember, are the separable solutions, right? We have found now the solutions of the time-independent Schrodinger equation. Let me go back to the iPad to write this now. Okay, so I go to the iPad and I share that. Okay, so we have now solved the time independent Schrodinger equation, okay, which is that the Hamiltonian acting on the function psi n of x is equal to en times psi n of x. Okay, so we know these guys. Okay, these functions are these Hermite polynomials times the exponential factor. And we know these energies, that these energies are n plus a half h bar omega. Okay, but that is not yet the full solution that we were hoping for, right? I mean, this is the hard part, but it's not quite the end of the story, okay? So now we have to remember the time-dependent separable solutions are the uppercase psi as a function of x and time, right? Which are these things that we have found times the time-dependent exponential factor, right? Where this energy is the same thing as that energy. So once we have, these lowercase psi's and these energies, right? That's the information that we need to get the product, right? And so that gives us the uppercase psi's, right? Which depend on both position and time. Okay? So that part is just like what we had with the particle in a box. Okay? And then the other thing that you need to remember is that the general solution is a combination. The general solution is a linear combination, that means a sum, of the special solutions times coefficients. Okay? So that is a general solution as a function of x and t is the sum over n values of some Cn coefficients times psi n of x times the exponential of minus Ent over h bar. So these are coefficients that say how much of each of the states do you have in the mix, right? Like making a recipe, how much of each ingredient do you have that goes into the mix, right? And for the sum, here we have to say, well, what values of n are we summing over? And it is, all the possible values of n. Now here is one tiny little difference from the particle in a box, okay? Because for the harmonic oscillator, our numbering starts with state number 0, right? There's a state number 0 and then number 1, number 2, number 3, okay? And so that means this sum has to be n equals 0 to infinity, right? So it's all integers from 0 on up, 0, 1, 2, 3, etc. Okay, so that means that if we want to know how a general solution evolves in time, we have to say, what are the Cn coefficients? Okay, so let's look at an example of that in Mathematica. Okay, so I'll switch back. So I stop the iPad and start Mathematica. Okay, so here is the Mathematica code, right? That corresponds to what I just wrote by hand, right? That the general solution is the sum of a Cn coefficient times the time independent special solution times the exponential factor of negative I energy of n times time over h bar. Okay, and that is summed for n equals 0. Well, in principle, it goes up to infinity, but here I'm stopping at 7. Okay, so here is a sum of 8 terms like that, right? From n equals 0 up to n equals 7. Okay, good with that? Okay. And then I need to know what is psi star, the complex conjugate, right? Well, so here it's the sum of Cn times psi n times this exponential now with a plus I instead of a minus I. And I really should have said the complex conjugate of the C's, because in principle, those things can be complex. So I say conjugate of Cn, like that. Okay. So this is a sum of a whole bunch of terms. Okay. Then the probability density is the product of psi star times psi. So a whole lot of terms times another whole lot of terms. Okay, so this is nice to have a computer to do these things. Okay, so let's do an example. Okay, so here I'll make an example where C0 is 1 over root 2 and C1 is 1 over root 2 and all the others are 0. Okay, so this is a combination with equal parts of C0 and C1, right? Equal parts of state 0 and state 1. Right? And so if I put that into the code and simplify, right, I get these terms, right? There's a term that involves the state 0 part squared. There's a term that involves the state 1 part squared. And there's a cross term. Right? And just as we saw in the particle in a box, right, the cross term has some time dependence, right? That the individual states are stationary, they don't depend on time, but when you have a cross term, you do get time dependence. Right? So let's see what a movie looks like. Okay, so here's a movie of that combination. Okay, and you can see that this this looks a lot like my game of Pong, right? In the particle in a box case, right? That we have probability that's going back and forth between the two sides, right? It's sloshing back and forth periodically, like a harmonic oscillator, because it is a harmonic oscillator, right? It's very similar to the particle in a box. The difference is just that there aren't hard boundaries on the side, right? And so the probability becomes extremely small, but it doesn't actually go to 0 when you have large X. Let's do another example where there are equal parts of state 1 and state 3. Okay, so excuse me, I meant state 0 and state 2. For state 0 and state 2, okay, but none of state 1. Okay, so now the movie looks like this, right? And so now the probability is sloshing back and forth between the middle and the sides, right? And that happens periodically. Right? Or how about if it's none of state 0, but there's state 1 and state 2. Okay. So if I make that to be 0, and here's state 1, and this makes this kind of complicated looking thing, right? But it is varying periodically, and the probability is sort of going from side to side, but with multiple peaks. And then we could calculate averages of things, right? And so if I want to calculate the average of X in this state, let's do that. Okay, so I could say the average X in this state, that would have to be an integral of, well, psi general star, okay, so that, what did I call it? Yeah, this thing, psi star general, okay. So I want to do this kind of integration, and I'll put an X in the middle of the sandwich, and I'll put in all my assumptions for all these coefficients. All right, and let's integrate that for x from minus infinity to infinity. And in order to do this integral, I have to put in a whole bunch of assumptions about what's positive, like this. If I didn't have these assumptions, then the software wouldn't know whether the exponential is decreasing or increasing at large x. Okay, is this going to work? Maybe, I hope. This is one I didn't practice in advance, so let's find out. There are really a lot of terms here, so it might take a long time to do. Well, maybe I'm going to get bored waiting. Okay, I'm going to get bored waiting. It'll come along. Okay, I'll let it run, and then I'll tell you something else while it's running. Okay, and we'll come back. Let me tell you something else, okay? So you see from this that this, oh, there's the answer. Oh, here's the answer. X looks like it's a cosine going back and forth, right? That's kind of like a simple harmonic oscillator, right? That you learned about in classical mechanics. Good, good. Now, you can see from this little exercise that the C coefficients are really important, right? That they tell you how much of each state you have in the mixture. So then you're wondering, well, how do you know what the C coefficients are, right? And here I was just making them up, which I can do because I'm the professor, right? But in an actual problem, how do you know what the C coefficients are? Okay, so let's talk about that. Okay, so I'll go back to the iPad. iPad. Okay, in an actual problem, let's find out. Let's ask. What are the Cn coefficients? Okay. These are determined in just the same way that we had for the particle in a box. Okay, that is, they have to be determined by the initial conditions. So any general solution with any Cn coefficients, right? Anything like this automatically satisfies Schrodinger's equation because that's how we set it up. Right? And there aren't really boundary conditions here, right? I mean, it goes all the way out to x equals infinity. You could say there are boundary conditions that the function is normalizable at infinity. Fine, okay, so this automatically satisfies those things too, okay, for any C coefficients. But for a specific initial condition, that only works with the right C coefficients. Okay. So how do you get from the initial condition to the C coefficients? That again works in just the same way as for the particle in a box, right? That is, there are the different possibilities depending on how lucky you are, right? That is, if you are very lucky, the initial condition exactly matches one state. So maybe the initial condition is that psi of x and time t equals 0 is equal to our wave function 169 of x, right? So that means you don't have to do any work, right? That tells us that C 169 is equal to 1, and all other CNs are equal to 0. Okay. So then we're all set. So then we can put that into this kind of equation, and then we'll know what happens into the future. Okay, in the future, we will, okay. In the future, we will have that psi of x and t is psi 169 of x times the exponential of minus I e 169 t over h bar. And this E169 is equal to 169 plus a half h bar omega. Okay. So that's if you are very lucky, okay? If you are medium lucky, then your initial condition matches a linear combination of a few of the size. A few of those things. So that tells us that there's just a few of those states in your mixture. Okay? So that could be that psi of x and 0 is, for example, 1 over root 2 psi 169 of x plus 1 over root 2 psi 170 of x. I don't know why I'm doing those numbers, okay? Just any old numbers. Okay, so these are the numbers for C169, C170. All other CNs are equal to 0. Okay, so it's not quite as simple as the last case, but it's still pretty simple. Okay, and then you know what happens in the future. So psi of x and time t is going to be 1 over root 2. Let's see. Oh, here. I wrote uppercase size. I meant to write lowercase size there because those are the time independent things. Okay. So 1 over root 2 psi 169 of x exponential of minus e 169 t over h bar plus 1 over root 2 psi 170 e to the minus I e 170 t over h bar. Okay. That's not too bad. Now, of course, here comes the third case. Okay, what if you are unlucky? That is to say that the initial condition is some other function. So it doesn't look like any one of those things. It looks like, I don't know, something totally different. Okay, there's all kinds of functions out there in the world. That means, okay, we have psi of x in 0 is some f of x, right? Some arbitrary thing like that. You remember what we did for the particle in a box in that case, okay? In that case, we took the arbitrary function and wrote it as a sum of sines. That's a Fourier series. Okay? Here, we need to do something like that again. Okay. We need to say, well, let's write out, what is this psi x and 0, right? So if we take our general psi over here and we plug in time equals 0, okay, then this factor is just 1. Okay? So psi of x and 0 is the sum, or n equals 0 to infinity, of Cn lowercase psi n of x. All right, that has to be equal to f of x. That means that we are going to express f of x as a sum of the psi n functions. Okay. Now, maybe you're thinking, wait a minute, that only worked for the particle in a box because the psi n functions were sines. And you can express any old function as a sum of sines based on Fourier's principle. Amazingly enough, that works for our new psi functions also. Okay, the same trick with the Fourier series also works for harmonic oscillator solutions. And we will see this semester that it always works for solutions of the time-independent Schrodinger equation. For all quantum mechanics problems, it works, right? That is amazing but true, okay? And so this business of expressing a function as a sum of the psi n functions actually works the same way, even if the psi n functions are not sines, but they are solutions for Schrodinger's equation in any quantum problem. Okay, and we do it by using Fourier's trick, right? So I'll say the analog of Fourier's trick Okay, so step one here, I'll copy this onto the next slide. Okay, so step one is multiply both sides by one of the psi of x's. I'm not going to say n because I'm already using the letter n. So I'll say psi L, right? This is my script letter L, which is any integer. Okay, so I'll multiply both sides. So, and in fact, I'm going to put a complex conjugate star here. It doesn't really matter because these things are real functions, but someday later in the semester it'll matter. So I'm going to say it for now. Okay. So I'll multiply both sides by this psi L star. Okay. So that means the sum n equals 0 to infinity of Cn times psi L star of x, psi n of x, is equal to psi L star of x times f of x. And then step two is integrate from x equals minus infinity to infinity. Okay, so on the left side, I have a sum from n equals 0 to infinity of Cn integral minus infinity to infinity psi L star of x psi n of x dx. That is equal to integral from minus infinity to infinity of psi L star of x f of x dx. On the left side, maybe you expected to see the integral out here in the front, but it doesn't matter because I can factor a sum out of an integral, and the c coefficients don't depend on x, so they can also be factored out of the integral. So let's put the integral here. Okay, and then step 3 is do the integral here. Now, you remember, right, when we were working with the particle in a box, right, this kind of step was an integral of two different sine functions, right? Which might have the same thing times x or different things times x, okay? And you remember that this integral gave us 1 if n equals L and 0 if n is not equal to L. Right? Amazingly enough, the same thing is true here with these functions. Okay? Amazingly enough, this integral is equal to delta Ln. Now, the textbook has a mathematical proof of that. Okay? I'm not going to give you the mathematical proof. Instead, I'll just show you that it works in Mathematica. Okay, so I'll go back to my Mathematica just briefly, and whoops, oh, I have to stop that and share. Oops. Share the Mathematica. I need a faster way to go back and forth. Does that work? Yes. Do you see the Mathematica now? Okay, good. Okay, here, I told Mathematica to make a great big table, okay? And so in the table, I take the conjugate of psi, well, here, instead of L and N, I called it N1 and N2, but same thing, okay? To make a table for different values of N1 and different values of N2. And so I'll take the conjugate of psi of N1 times psi of N2 and integrate it for x goes from minus infinity to infinity. And sure enough, it checks out, right? That if we have psi 0 times psi 0, that integrates to 1. If you have psi 1 times psi 1, it integrates to 1, right? If you have psi 0 times psi 1, it integrates to 0, right? Any product of different size integrates to 0. And any product of the same size integrates to 1. Okay. So that is a very handy trick. Okay. Let me tell you a vocabulary word that goes with that trick. Okay. Are we back on the iPad? I think my computer is slowing down. Okay, here it is. One vocabulary word is to say orthogonal functions. Okay, that means that the integral of psi L star of x times psi n of x dx is equal to 0 for L not equal to n. Right. So to say things are orthogonal functions means that if you have different indices, L and N, that are different from each other, you get 0 when you combine them in this way. Okay. Another vocabulary word that goes with this is normalized functions. And you already know about that, right? You know that the integral from minus infinity to infinity of psi n star times psi n is equal to 1. Okay. We've been talking about that all semester, right? So that's normalized, right? So that's what happens when the indices here and there are the same. Okay. Now, it often happens that people deal with some set of functions that have both of these two properties, right? That if you combine the same function in the set, like this, you get 1. And if you combine different functions in the set, you get 0, okay? And so that happens often enough that we get a combined word. People make the word orthonormal functions, which means orthogonal and normalized. So that means that the integral like this of psi L star of x times psi n of x dx is equal to this delta ln, right? So it's equal to 1 if L equals n and 0 if L is not equal to n. Are these vocabulary words that they presented in your math classes? Maybe, yes, okay. I mean, this works for vectors also, right? This could have come in with vectors, but it works with functions, and I'll be talking later about connections between vectors and functions. Okay, so with that fact, okay, that the solutions of the harmonic oscillator are orthonormal. Okay, so then we can go back to this integral right here. Okay? So this integral then gives us that the sum from n equals 0 to infinity of Cn times delta Ln is the integral on the right side, which is this thing, the integral from minus infinity to infinity, psi L star of x times your initial condition times dx. Right? And now with this sum over here, this is exactly the same story as we had for the particle in a box, that in this sum, it's an infinite number of terms, but only one of them is non-zero, right? Only the term where n equals L is non-zero. Every other term in that sum is 0. So the only term that's non-zero is when n equals L. So this is, CL. That is this integral over here. Okay, so this then gives us an equation that we can use to determine the C coefficients. Okay, so if we start with any arbitrary initial condition, okay, and we know these solutions, then we multiply those things, integrate over x, right? That would give us the CL coefficients. And then if we have the CL coefficients, then we know the general solution, psi of x and t, right, which is the sum of the C coefficient times psi n of x times its exponential factor. And as always in quantum mechanics, right, once we know the wave function, then we know everything that we can know, right? And so then we can calculate probability densities and make movies of them, and we can calculate expectation values, right, for position or momentum or energy or whatever we want. So that is my story about the harmonic oscillator. Okay, so that's the the theme of this week, and I finished it with 5 minutes to spare. Wow. Okay, so that's for this week. Okay, is the harmonic oscillator, which is another example of a quantum mechanics problem. Okay, and so now you know two examples, right? You know particle in a one-dimensional box, and you know a harmonic oscillator in one dimension, okay? And you can see what's similar and what's different about them, right? You can see in each case, there's a set of quantum states, and each state has its own energy. And so you get this general solution that's a combination of these different states and the time-dependent exponentials, right? And we get what are the solutions for the size, what do those solutions look like? And they are different functions, but the functions actually have some similarities if we look at the plots, right? And so we can sort of tell from looking at a plot what's a higher energy or a lower energy state. Okay, so this is a lot to take in, and so you do need to do some practice problems just to absorb all of this. And so I did post a new homework on that. So we'll say homework number 3 is posted on the Google Drive. And it is due a week from today. So that is February 18th. And homework number 2 is due today. So please send that to me today if you have not already done so. Some of you have already done so. Okay, I think we're good for now with the harmonic oscillator. And so next week I will start off with a different kind of quantum mechanics problem. So a problem that is, it's actually simpler in calculations, but it has some conceptual variations. And so we'll get started with that. So just the problem of a free particle. And so that's discussed in the next section of the textbook, and I'll be presenting that starting on Monday. Okay, so have a good weekend, you guys, and I'll see you on Monday, but of course I'll stick around if you have any questions. All right, thanks, bye.